Welcome to topic 3 of the gas laws. Letter E, the combined gas law. The combined gas law is a mathematical combination of Boyle's, Charles, and Gay-Lussac's laws. The combined gas law, sometimes known as CGL, expresses the relationship between pressure, volume, and temperature of a fixed amount of gas. Here's the equation for the combined gas law. P1 V1 over T1 equals P2 V2 over T2. The subscripted 1's on the left side of the equation represent the initial conditions of the gas. The subscript 2 variables on the right side of the equation represent the final conditions. Just like with Charles and Gay-Lussac's laws, temperature must be in Kelvin if using the combined gas law. Here's an example problem. An oxygen-filled flexible container has a volume of 50.0 liters at a temperature of 25 degrees Celsius and a pressure of 1.00 atmospheres. What is the temperature of the oxygen gas if the volume of the container is expanded to 60.0 liters, while the pressure is being decreased to 0.855 atmospheres? Because you have some previous experience with the gas laws, we'll walk through this pretty quickly here. The equation is given, P1 V1 over T1 equals P2 V2 over T2. We're going to substitute in all the given variables. There'll be one unknown variable left. Remember that we have to use Kelvin temperature, so I'm quickly going to convert from 25 degrees Celsius to 298 Kelvin by adding 273. I'm now going to substitute in all my known variables. The original or initial pressure was given as an atmosphere. The original volume was 50.0 liters, and the original temperature was 298 Kelvin. The pressure dropped to 0.855 atmospheres, while the volume was expanded to 60.0 liters. The final temperature, T2, is my unknown variable. I'm going to cross multiply in order to get rid of this fraction. And then using algebra, we'll be able to solve for T2, the final temperature. Notice that as you cross multiply, I'm keeping track of all of the labels. This will help me at the end to make sure that I have the problem set up correctly. I'm going to divide both sides by 1 atmosphere and 50 liters in order to isolate the variable T2. That's our unknown. You'll see on the right-hand side of the equation, both atmospheres and the label liters will be canceled out. This is only going to leave Kelvin as the available unit, which is a temperature unit. That means we do have this problem set up correctly. Using your calculator and sig fig rules, you'll round off your answer to 306 Kelvin.